Did you know that a single farmer in the United States today can feed more than 160 other people? While agricultural workers make up only about 1% of the population, the U.S. still operates one of the largest and most efficient food systems on the planet. How can such a small workforce control an entire global chain of production, distribution, and agricultural standards? In this video, join Agriculture Insight as we explore the core technological pillars behind U.S. agriculture, where technology doesn't just replace human labor, but reshapes how the world produces food. In the 1930s, the United States faced the risk of a collapse in its food system due to failures in land and climate management. The Dust Bowl was triggered by large-scale overcultivation combined with prolonged drought cycles, stripping away millions of tons of fertile topsoil, turning vast agricultural regions into wastelands, and forcing more than 2.5 million people to abandon their homes. This shock compelled the United States to fundamentally change its development mindset, from short-term exploitation to systematic resource governance. The government reorganized land use into specialized agricultural belts and implemented strict soil conservation standards to mitigate long-term risks. As a result, the vast geometric fields stretching hundreds of kilometers across the United States today are not a geographical coincidence, but the direct outcome of a nationwide agricultural restructuring, laying the foundation for the high-efficiency production model the country operates today. On average, a farm in the United States spans several hundred acres. But in major grain belts, such as Iowa and Nebraska, farm sizes often surge to around 2,500 acres, equivalent to nearly 2,000 football fields combined. As a result, efficiency at this massive scale becomes an unforgiving challenge. A steering deviation of just a few inches can waste tons of seeds due to overlapping rows, or cause heavy machinery to crush crops that are already growing. This is why many large farms in the United States have now transitioned to GPS RTK technology, one of the key innovations propelling the country directly into the era of precision agriculture. At its core, while conventional GPS positioning operates with errors of several meters, RTK in the US follows a fundamentally different principle. The technology relies on fixed ground-based reference stations to measure and eliminate satellite signal disturbances, continuously transmitting real-time correction data to tractors in the field. As a result, errors caused by atmospheric interference or satellite clock drift are effectively removed, reducing positioning accuracy from arm-length margins to just over 1 centimeter, roughly the width of a fingertip, across enormous fields. Thanks to this technology, a bulky tractor can now operate like a true robot. It not only eliminates overlapping seeding, but can also return precisely to the same wheel tracks from previous seasons, an advantage that helps reduce input costs and protects soil structure from excessive compaction caused by new tire paths. With upfront investments of at least $10,000 USD per unit, along with annual signal subscription fees, RTK has become a mandatory expense for maintaining competitiveness in large-scale agriculture. For decades, American farmers have been trapped in a vicious cycle. Weeds grow increasingly resistant to herbicides, forcing higher chemical dosages that degrade soil structure and trigger consumer backlash. As environmental regulations tighten, carbon robotics introduced a game-changing solution: the laser-powered weed-killing robot. This machine is essentially a mobile supercomputer fused with heavy industrial mechanics. As it moves across the field, a system of 30 industrial cameras continuously scans the ground. Within milliseconds, an AI processor analyzes the data and isolates targets, smart enough to distinguish young crop seedlings from weeds, even when they grow intertwined. Once a target is confirmed, high-power laser units fire ultra-short thermal pulses directly at the weed's growth point. Weed cells are destroyed instantly, without heating the soil or touching a single leaf of the crop. With a processing speed of up to 100,000 weeds per hour, a single machine can replace the labor of a 50-person workforce. However, the biggest barrier to adoption is its price tag, up to 1.4 million USD, a risky investment without sufficient scale. Yet for farms spanning thousands of acres, the robot's ability to operate continuously through the night becomes the decisive advantage in the race against time. As chemical and labor costs continue to rise, this robotic system not only enables cost recovery within 2 to 3 growing seasons, but also opens a viable path toward large-scale clean agricultural production, something that was previously considered impossible. Beyond leading the world in tractor production, the United States dominates more than 40% of the global market for smart agricultural equipment. With over 450,000 combine harvesters currently in operation, the U.S. runs one of the largest harvesting systems on the planet, structured around strategic grain crops such as corn, soybeans, and wheat. Yet the true advantage lies not in sheer scale, but in how these machines optimize themselves while working. High-capacity harvesters from John Deere and Case IH, the two pillars dominating the North American large harvester segment, employ automated axial threshing systems driven by algorithms. As the machine operates, onboard systems continuously analyze grain flow, moisture levels, and loss signals, automatically adjusting concave clearances and airflow in real time. This keeps harvest losses at the lowest economically viable level. Combined with ultra-wide cutting headers, reaching record widths of up to 18 meters, and synchronized logistics systems, where grain carts run alongside the harvester to receive output without forcing the machine to stop for even a second, American harvesters can achieve throughput levels of around 70 tons per hour. This is the fundamental distinction from many European machines, such as those produced by Claas, which prioritize flexibility for smaller fragmented fields, while American machines are engineered to dominate vast, open plains. The race in high-tech agriculture does not stop on the ground. The aerial front also clearly bears the imprint of the United States. With fixed-wing drones, American farmers have successfully monitored and sprayed vast megafarms spanning thousands of acres. Rather than relying on permanent infrastructure, these systems operate like mobile field units, deployed directly from mobile hangars positioned at the edge of the fields. The process begins with a reconnaissance phase. Flying at high altitude, multispectral sensors scan the entire area, allowing AI systems to construct digital maps and isolate pest and disease hotspots. This is followed immediately by the strike phase, in which drones autonomously return to treat precise target coordinates, instead of wasting chemicals through blanket spraying as in traditional methods. Crucially, traveling at speeds of 90 to 120 kilometers per hour, the long wingspan generates powerful downwash airflow that forces spray droplets through dense crop canopies, ensuring adhesion all the way down to the base of the plants. This mechanism not only reduces chemical usage by up to 60%, but also enables U.S. agricultural products to more easily meet the stringent residue limits imposed by the Food and Drug Administration. Amid an increasingly severe shortage of arable land, a new production model is now emerging inside abandoned warehouses and even high-rise buildings across the United States. Although the number of such farms is smaller than in Japan, the U.S. hosts the largest vertical farming complexes on the planet. In New Jersey, the East Coast's leading high-tech hub, an AeroFarms facility occupying less than 2 acres delivers yields equivalent to up to 200 times those of traditional farmland. To replace sunlight, LED systems emit precisely calibrated red and purple wavelengths, the two spectra that most strongly stimulate chlorophyll without wasting energy. By maintaining continuous 24/7 illumination, crops are fully decoupled from natural variability while sustaining uninterrupted growth. However, lighting alone solves only half the equation. The real advantage lies in a fully automated operating system, Robots work in tandem with multi-level conveyor networks, moving continuously both horizontally and vertically. This constant circulation eliminates environmental blind spots, ensuring that every cubic meter receives uniform care, an essential factor for maximizing yield within a fixed footprint. Even so, the model still faces significant operational cost challenges, particularly the massive energy demand required to maintain a closed-loop system. In return, a lettuce crop that takes 45 days to grow outdoors can be harvested here in just 14 days. More importantly, production is relocated directly to consumption centers, eliminating thousands of miles of interstate transport and allowing produce to move from rack to supermarket shelf within hours. If vertical farming represents fully enclosed agricultural factories, then in cities like New York and Oakland, another revolution is unfolding at the very top of urban buildings. More than 500 farms are now greening industrial rooftops, an approach that transforms thousands of acres of abandoned concrete into productive systems, delivering yields up to 10 times higher than traditional farming. The greatest challenge in bringing agriculture to rooftops is structural load. To solve this, engineers eliminate natural soil entirely, replacing it with ultra-light engineered substrates, a blend of porous mineral aggregates and organic compost. This specialized structure allows a 30-centimeter growing layer to deliver maximum oxygen to plant roots, while keeping the total system weight to just 1/3 of conventional methods. Operationally, these farms function as a smart hybrid between soil-based cultivation and hydroponics. Nutrients are managed through fertigation technology, which injects organic nutrient solutions directly into drip irrigation networks. This enables vertical intercropping techniques, for example, planting fast-growing lettuce between rows of longer-cycle crops, such as cabbage. By optimizing every square inch of available space, a rooftop farm of just over 1 hectare in Brooklyn can supply up to 9 tons of food annually. More importantly, all produce is harvested and distributed the same day to nutritionally underserved neighborhoods, turning idle concrete rooftops into critical food security infrastructure. Fresh produce, however, represents only the visible layer of value. The deeper strategic benefit lies in urban regulation. By absorbing millions of liters of rainwater each year, these systems directly reduce pressure on municipal drainage networks and lower building temperatures by up to 5 degrees Celsius during summer months. For this reason, despite high upfront investment costs, the combined gains in energy efficiency and atmospheric control establish long-term value, transforming buildings from passive structures into active systems capable of self-regulation in the face of increasingly extreme climate conditions. Behind the massive volumes of corn destined for industrial processing, the vast fields of central Illinois also produce 60,000 tons of silage corn each year, directly boosting herd productivity and shaping the richness and consistency of every glass of milk. The golden window for harvesting silage corn arrives in late summer to early fall, when the entire plant reaches optimal maturity. Having stored sufficient energy while retaining around 30% moisture, the ideal level for dense packing and stable fermentation. Once this biological threshold is reached, the entire field immediately shifts into the continuous rhythm of massive harvesting machines. Corn stalks are cleanly cut, the entire biomass is finely chopped and blown directly into trucks moving in parallel, keeping the material flow seamless and protected from air exposure. Thanks to this uninterrupted chop and blow process, each machine can handle 600 to 650 tons per hour, allowing the entire harvest to be completed in just a few days before colder weather sets in. From the field, the chopped corn is transported straight to the silage site at peak freshness. Here, the silage mass is spread in thin layers and continuously compacted by heavy machinery weighing dozens of tons. This pressure forces oxygen out, creating an anaerobic environment in which the sugars within the biomass are converted into lactic acid, the foundation that keeps the silage stable throughout the winter months. After about 3 to 4 weeks, fermentation is complete. Chlorophyll breaks down, dry matter increases, and the vibrant green gradually shifts to a beige-yellow hue. The silage is then tightly sealed, ready to be opened during the cold season, characterized by a mild acidic aroma, soft fibrous structure, and the absence of mold. Few realize that milk from cows fed on corn silage is typically richer in fat, rounder in flavor, and noticeably less acidic than milk produced from dry hay-based diets. This is due to easily digestible starches that release energy steadily in the rumen throughout fermentation. In other words, milk quality is largely determined at harvest, long before the cow ever enters the milking parlor. Despite being widely blamed as a leading cause of weight gain, in Idaho, the potato capital of the United States, more than 6 million tons of potatoes each year still enter the massive machinery of harvest. Peak harvest season begins in late September, when the cold nights of early fall force starch to retreat fully into the tubers. At this stage, dry matter and solid content reach their ideal levels, just before the soil begins to freeze. Once the foliage has died back, harvesting machines roll into the fields. Rather than overturning the soil, the digger system lifts an entire layer of earth, about 8 to 10 centimeters thick, raising the full potato row onto a conveyor, while the tubers remain coated in moist soil. Multi-level vibrating belts then use gravity to separate soil, roots, and stones, while harvesting speed is constantly adjusted to minimize impact on the skins. Potatoes are not dumped in bulk. Instead, they are gently cushioned and evenly distributed within the holding bin, then transferred laterally into trucks moving alongside, allowing the entire operation to run without stopping. From the moment they leave the ground, most of these potatoes are already destined for fries, chips, and frozen potato plants. However, only 40 to 50% of the harvest meets the strict standards for size, shape, and dry matter required for premium fry production. Harvest, therefore, is not merely the end of a growing season. It is the starting point of a familiar cycle, one in which potatoes become the king of starch, a food Americans both wary of and unable to resist. Just before snowfall arrives, clementine orchards across Spain burst into color. As the thin skins on the trees turn a deep orange, taut, evenly ripened, and faintly scented with their signature citrus oils, farmers step into the groves wearing large harvesting bags capable of holding dozens of kilograms of fruit. This allows them to move continuously between rows without frequent returns to collection points. Fruits growing on the lower branches are picked with a gentle twist at the stem, right at the natural separation point, preventing skin tears and minimizing sap release that could dull the surface. For higher clusters, lightweight aluminum ladders about 2 to 3 meters tall are placed close to the trunks, extending reach while protecting young, fragile branches, crucial for maintaining yields in the following season. Despite annual production approaching 2 million tons, the majority of Spanish clementines are still harvested entirely by hand. This method preserves the fruit's shape, skin tension, and balanced sweetness, key standards demanded by discerning markets such as the UK, Germany, and Northern Europe throughout the winter citrus season. Every Christmas season, more than 2 million tons of chestnuts are consumed worldwide, appearing at street-side roasting stalls, in home kitchens, and on winter dining tables. But have you ever wondered how these chestnuts are harvested before releasing their signature aroma in the roaster? Starting in September, when growth pressure accumulated throughout the summer reaches its peak, chestnut burrs naturally split open and drop straight to the ground, an unmistakable signal that the harvest season has begun. In small family-run orchards, where chestnut trees are favored for their long lifespan, cold tolerance, and low maintenance, harvesting still relies almost entirely on manual labor. Harvesters use specialized tongues to pick up each nut from beneath the trees, avoiding injury from the sharp, spiny husks. Though slow and physically demanding, this method allows for immediate selection in the orchard. Only round, glossy, uncracked, mold-free chestnuts are kept. Key criteria ensuring the nuts are sweet enough, dry enough, and ready to move directly into the market. However, in large-scale growing regions such as Tuscany, more than 50,000 tons of chestnuts must be collected within just 72 hours each season. A massive volume that quickly exceeds human limits and turns the entire harvest into a race against time to prevent moisture absorption, fermentation, and internal mold. As a result, mechanized systems become the operational core of the orchard. At the heart of these machines is a ground-hugging elastic sweeper driven by a precisely calibrated hydraulic rotating shaft, soft enough to glide over leaf litter, spiny husks, and shallow roots, yet strong enough to flick heavy round chestnuts into the collection flow. Immediately behind it, a high-powered suction system creates a strong pressure differential, pulling the nuts into the machine while soil, stones, and heavier debris are rejected directly at the intake. Thanks to this integrated sweep vacuum screen design, each machine can process up to 4 tons of chestnuts per hour, the equivalent of dozens of manual workers, but more importantly, fast enough to capture the narrow golden window of the harvest. From here, mechanized harvesting has become the new standard in modern facilities, where chestnuts are sorted, heat-treated, or frozen, then transformed into a wide range of products for the busiest season of the year. Known as the purple gold of southern France, the perfectly aligned lavender fields enter the decisive moment of their entire growing cycle as early as the start of summer. From the first weeks of the season, specialized harvesting machines begin rolling along the rows, cutting close to the stems at precisely calculated heights. The blades oscillate at high frequency, fast enough to slice cleanly through each flower cluster, yet accurate enough to preserve the tiny oil sacs within. Even a slight deviation can cause an entire batch to lose its value. Immediately after cutting, the lavender tops are vacuumed directly into rear-mounted containers, barely touching the ground. Within minutes, a ribbon of purple stretching hundreds of meters disappears, leaving behind bare stems, ready to regenerate for the next season. As soon as the harvest leaves the field, the lavender is transported straight to distillation facilities within hours. As any delay under the summer sun leads to immediate losses. Thanks to high concentrations of linalool and linalool acetate, lavender essential oil delivers a warm, soothing, deeply relaxing effect. Stored from summer to become the base note for scented candles, room diffusers, and calming therapies throughout the colder months. Just by looking at Akatsuki, Japan's national peach variety, it's easy to see the country's uncompromising standards in agriculture. By July, when the fruit reaches perfect ripeness, each peach appears smooth, evenly blushed, and plump, the result of nearly a full year of meticulous care. Weeks in advance, every fruit is wrapped in a paper bag to control insects, weather exposure, and sunlight, ensuring uniform skin coloration. When harvest season arrives, peaches are picked entirely by hand. The stem is held, the fruit is gently rotated once, then cleanly detached and placed individually into trays, never stacked, with zero margin for error. This strict attention to detail pushes Akatsuki peaches to prices of up to $50 per fruit, comparable to a serving of A5 Wagyu in Tokyo. Rather than chasing volume, Japan has chosen a different path, breeding hundreds of peach varieties for the premium market, built around standards that far exceed the global average. As autumn arrives in Washington state, pear orchards reach a stage of firm, mature green, an indication that starches have fully converted into sugars and accumulated within the flesh, while softening enzymes remain largely inactive. This delicate balance forms the critical foundation for the fruit's ability to ripen properly after harvest. To preserve this fragile state, growers harvest pears at the technical maturity stage. Each fruit is cradled in the palm, lifted along the stem axis, then twisted decisively to detach from the branch, minimizing pulling force and surface impact. This technique is especially crucial for thin-skinned European pear varieties such as Bartlett, Anjou, and Bosc, which are highly sensitive to mechanical damage. Immediately after leaving the orchard, the pears are rapidly cooled and sorted in packing facilities before the ripening process can self-activate. It is this short, continuous, closed-loop operation that allows Washington to maintain its position as the nation's leading pear supplier, producing up to 300,000 tons annually, with a significant portion flowing directly into the canned pear industry, ensuring Washington pears remain available on supermarket shelves around the world year-round. In large-scale grape-growing regions, harvesting machines such as New Holland's Broad are purpose-built for trellised berry crops. By simply swapping the shaker units and collection trays, the same machine platform can be adapted to multiple grape varieties. Its high-clearance chassis and well-balanced center of gravity allow stable operation between vine rows, even on sloped terrain. Rather than cutting or picking, the machine uses a vibration mechanism operating at 400 to 500 shakes per minute to detach ripe grapes, while elastic rollers and controlled airflow remove leaves, stems, and debris before the fruit enters the bins, minimizing bruising. Each machine can harvest over 20 tons of grapes per hour, equivalent to dozens of manual workers, forming the backbone of industrial wine and juice production, where speed and uniformity take priority. However, for premium grape varieties destined for high-end winemaking and the fresh export market, harvesting is still carried out entirely by hand. In California, when grape clusters turn deep purple and develop their natural white bloom, hundreds of workers spread across the vineyards, each holding small, razor-sharp shears to cut clusters one by one. Once removed from the vine, every bunch is inspected for skin integrity and potential damage before being gently placed into shallow, crush-resistant trays. Thanks to this meticulous approach, California continues to produce over 6 million tons of fresh grapes each year, forming the backbone of both its premium wine industry and its global fresh grape exports. From May to July each year, the cucumber fields become more vibrant than ever as the harvest season officially begins. On the vast fields stretching endlessly, modern machines, large, precise, and powerful, have become the extended arms of farmers during the busy season. As the machine moves along each row of cucumbers, the harvesting head functions like a giant comb, brushing through each stem and guiding the vines into the machine. Inside, an automatic sorting system removes unnecessary leaves and stems while only keeping the cucumbers that meet the standards and transferring them to the conveyor belt behind. Unlike the modern potato harvesting machines from Grimm or John Deere, which are designed to dig up soil and separate potatoes from the ground with a capacity of up to 20 tons per hour, cucumber harvesting machines are built to be lighter and more precise, allowing them to harvest cucumbers without crushing the fruit. With a capacity of around 5 to 10 tons per hour, Traditional farming still yields stable cucumber harvests, but relies heavily on chemicals. In this context, organic farming, hydroponics, and greenhouses are gradually becoming the trend due to their ability to optimize yield, minimize negative environmental impacts, and address consumer concerns about pesticide residues and herbicides. Although technology has advanced significantly, it is the diligent hands of workers that still bring superior quality that machines cannot replace. Workers carefully pick each cucumber by hand, selecting those that are ripe and of the right size, then place them onto a moving conveyor belt attached to the harvesting machine or specialized trailer, helping transport the cucumbers to the storage containers quickly and gently. Manual harvesting, although much less efficient compared to modern machines with a capacity up to 15 times higher, ensures the finesse and precision that machines cannot achieve. After harvesting, trucks quickly transport the cucumbers to processing factories within 2 to 4 hours, preserving their freshness, crispness, and texture before embarking on the next secret journey, becoming the tangy, crunchy pickles that captivate the world. At the pickle processing plant, trucks carrying millions of tons of fresh cucumbers line up one after another, entering the raw material intake area. In modern factories, cucumbers are introduced into a closed-loop washing system, with multiple stages designed to ensure food safety and high input quality. First, cucumbers from transport trucks are poured into large indoor water tanks. These tanks contain clean, continuously recirculating water, often treated with ozone, diluted chlorine, or light brine to eliminate surface contaminants. The gentle water flow helps rinse off soil and debris while moving the cucumbers toward the conveyor belt without causing any bruising. Next, the cucumbers pass through a high-pressure multi-directional spray tunnel, typically 4 to 6 bar, where powerful water jets thoroughly remove dirt and bacteria. The water used in this stage is filtered and reused through a closed system involving mesh filters, activated carbon, and UV or ozone sterilization, ensuring both hygiene and resource efficiency. This process doesn't fully eliminate pesticide or chemical residues, which may remain on the fruit's surface. Therefore, to ensure consumer health and safety, factories must conduct strict checks in addition to following farming standards. Modern methods like HPLC and MS detect pesticide residues with high accuracy, with residue levels ranging from 0.05 mg to 5 mg per kilogram, depending on the pesticide and regulations. Now here's where it gets interesting. There are 2 popular methods, each with its own secret formula for making pickles: natural fermentation for traditional and premium lines, and quick vinegar pickling for industrial products. First, for the natural fermentation method, cucumbers are sorted and then placed into large fermentation tanks, often positioned outdoors to take advantage of the ambient temperature, providing ideal conditions for fermentation. This method not only saves energy, but also promotes the growth of beneficial bacteria, which in turn creates the characteristic sour taste and increases the probiotic content in the final product. Each tank is filled with brine solution, a mixture of salt water and spices like dill, garlic, pepper, bay leaves, and others, depending on the unique recipe of each brand. The cucumbers are soaked in brine for 1 to 4 weeks, depending on the thickness of the skin, the type of product, and the desired flavor. It is the clever use of ambient temperature to promote the development of beneficial bacteria during fermentation, combined with the long soaking time, that is the key to creating the difference in flavor and crunchiness between the natural fermentation method and the quick vinegar pickling method. Once the fermentation period is complete, the pickles are carefully removed from the brine tanks and immediately transferred to the processing line for final cleaning and inspection. At this stage, each pickle is thoroughly rinsed to remove any excess brine, spices, or sediment that may have settled during fermentation. After rinsing, the pickles pass through a visual inspection system, either by trained workers or automated optical scanners, to detect and remove any defective or damaged pieces. Next, the pickles are sorted by size and shape using precision mechanical graders, ensuring uniformity in the final product. They are then transferred into filling machines, where they are packed into jars or food-grade barrels. Before sealing, each container is filled with a final brine solution, either the original fermented brine or a fresh one, prepared under sterile conditions, to maintain flavor and preservation. Finally, the sealed jars undergo pasteurization in hot water baths or steam chambers, depending on the product type and shelf life requirements. This step helps to stabilize the pickles, ensuring food safety while retaining their natural crunch and probiotic benefits as much as possible. In contrast, the vinegar pickling method takes only a few hours, meeting the enormous demand with billions of jars produced worldwide each year, and a longer shelf life, all while being about 4 times cheaper than naturally fermented products for the same volume. And this is why this method is so effective. After being thoroughly washed and sorted, the cucumbers are placed directly into pre-sterilized glass jars or plastic containers to ensure absolute hygiene. Before the cucumbers are added, dry spices such as dill, garlic, mustard seeds, black pepper, and bay leaves are added to infuse natural fragrance. The cucumbers are then automatically divided into the glass jars. In addition to whole pickles, many products are also sliced into rounds, cut into chunks, or shaped in various ways, perfect for topping McDonald's or Burger King's burgers, or served with salads and sandwiches at chains like Subway and KFC. After the cucumbers are divided into jars, they are moved to the brine filling area, where the soaking solution is added to complete the flavor and preservation structure of the product. The key difference in this step lies in one essential ingredient: vinegar. For industrial pickle products, due to the lack of natural fermentation time, the brine solution must include vinegar, acetic acid, at a ratio of 5 to 10%, combined with salt, sugar, and other spices. While the natural fermentation method requires refrigeration to maintain freshness and is typically consumed within a few months, vinegar provides an immediate sour taste. It also acts as a natural preservative, allowing the product to be stored at room temperature for up to a year or longer, making it more convenient for large-scale distribution in the global industry. For industrial pickle lines, this is also the beginning of the short fermentation process, which is strictly controlled for temperature and humidity, ensuring the product achieves a consistent flavor and standard crunchiness. So is naturally fermented pickled cucumber or quick vinegar pickled cucumber your idea of the perfect jar of pickles? The next step is pasteurization. Typically, the jars of pickles are placed in a continuous pasteurizer or high-pressure retort, where they are heated to a temperature between 80 degrees Celsius and 100 degrees Celsius for 10 to 30 minutes. After leaving the heat chamber, the product is rapidly cooled by passing through a cold water spray system, combined with high-powered fans placed along the conveyor belt, which helps quickly lower the temperature and prevent overheating or changes in the pickle's texture. Most naturally fermented pickles don't require pasteurization, as the fermentation process creates an acidic environment that inhibits harmful bacteria and preserves beneficial probiotics. Finally, the jars of pickles are placed on a conveyor belt, and pass through an automatic labeling system. Each label clearly displays the product name, ingredients, production date, and expiration date. This step ensures that all jars have consistent, accurate, and compliant information for distribution. Pickles not only play a vital role in the global economy, generating billions of dollars in revenue each year, but also serve as a cultural bridge, connecting diverse culinary traditions and bringing the distinctive sour flavor of 4,000 years of history to kitchens around the world. Grain sorghum, also known as milo, is a true jack-of-all-trades in the world of crops. Grain sorghum could be seen as the lively cousin in the family of grasses, with corn as the uncle and wheat as the aunt. This mighty crop stands tall like the legendary basketball player Shaquille O'Neal, reaching an average height of 5 to 12 feet. With its sturdy stalks crowned by clusters of grain-filled heads, it commands attention on its very own NBA Field of Fame. Its remarkable drought tolerance allows it to thrive in hot, dry climates, making it a vital crop for arid regions like Kansas, Colorado, Oklahoma, and Texas. Planting begins in late spring when soil temperatures hit about 60 degrees. Farmers use GPS-guided seed planters to ensure seeds are sown in straight, evenly spaced rows, optimizing land use. Automated machinery, such as smart sprayers, applies fertilizers and pesticides, while automated irrigation systems ensure healthy crop growth to maturity. Combining traditional wisdom with modern technology, American farmers lead in global sorghum production. Harvesting a colossal 20.9 billion pounds of grain sorghum each year is no easy task. But with the aid of modern machinery and the artistry of masterful farming, American farmers have transformed this monumental challenge into a symphony of precision, efficiency, and awe-inspiring excellence. After 90 to 120 days, in the fall, the time of triumph arrives as the grain sorghum matures, ready for harvest. In the first stage of sorghum harvesting, American farmers rely on their high-tech combines, machines that resemble the mighty chariots of the modern agricultural world. These mechanical giants, equipped with GPS and AI technology, sweep across the fields like unstoppable warriors, cutting through the thick stalks of sorghum with precision and power. With their finely tuned cutting depth and speed, they adapt seamlessly to the terrain, ensuring the perfect harvest while minimizing crop damage. These combines are not just machines. They're symbols of the resilience, innovation, and efficiency of American farmers. Now let's dive into the authentic sounds of harvesting in the expansive fields of America. If grain sorghum focuses on its seeds, then forage sorghum elevates the modern harvest operations of American farmers to an entirely new scale. Standing amidst the vast fields of forage sorghum, we become tiny specks in a smooth, green ocean, where nature and humanity merge to create a rural masterpiece, both majestic and bursting with life. Enter the forage harvester, a beast of a machine that makes combines look small by comparison. These powerhouses mow down the towering plants, chopping them into silage-ready pieces faster than you can say moo. Silage trucks follow closely, catching the fresh-cut forage like eager teammates in a well-choreographed relay race. The chopped material is packed into silos or bunkers, where it undergoes fermentation to become nutrient-rich silage, a wintertime delicacy for cows, sheep, and goats. And so, from towering plants to chopped silage, forage sorghum provides livestock farmers with an endless buffet of goodness. Together, grain sorghum and forage sorghum showcase the brilliance of American farming. Smart timing, cutting-edge technology, and a commitment to sustainability that ensures no part of the crop goes to waste. It's not just farming, it's a masterpiece of modern agriculture. When sorghum is harvested, combines gather the grain into large hoppers, ready to be transported to storage facilities. Nothing goes to waste. The remaining stalks, known as stovers, are processed directly in the field using specialized equipment. For those destined to become livestock feed, baling machines step in, compressing the shredded stalks into perfectly formed, dense hay bales. These bales, massive and uniform, are hauled to farms, where they become a vital, fiber-rich lifeline for livestock during the seasons ahead. This sustainable process reflects the wisdom of generations of farming practices, now enhanced by the marvels of modern technology. It's a harmonious blend of tradition and innovation that makes each harvest a powerful testament to the ingenuity and strength of American agriculture. These remarkable machines, often regarded as the unsung heroes of modern agriculture, stand as a lasting and enduring symbol of technological progress, environmental sustainability, and the unwavering dedication, ingenuity, and pride of American farmers, who work tirelessly to feed a nation while preserving the land for future generations. After leaving the farm, grain sorghum heads to processing facilities where it's transformed into a variety of products. Here's a behind-the-scenes look at what happens next. The journey of grain sorghum continues with a meticulous cleaning process. Specialized machines, such as air classifiers and vibratory screens, are used to remove any dirt, debris, or foreign materials that may have been collected during harvest. This ensures that only clean, high-quality grains proceed to the next steps. Once cleaned, the sorghum is sorted using advanced optical sorters, which scan the grains to classify them by size and color. Grains that meet the highest standards are separated from those that don't, ensuring only the best make it to the next stage. In the milling stage, sorghum grains are ground into flour or meal for various uses. The milling process begins with rollers, which crush and refine the grains in stages, breaking the husk and gradually reducing the particles to the desired size. Next, sifters separate the fine flour from coarser fragments, redirecting larger pieces for further milling. This precise combination ensures a smooth, consistent product while preserving the grain's nutritional value. This step is vital for creating gluten-free sorghum flour, which is widely used in baked goods and other products, making it a popular choice for individuals with dietary restrictions, particularly those who need gluten-free options. Finally, after being milled or processed into byproducts, sorghum grains are packaged and distributed to livestock farms. These gluten-free products or animal feed are sent to regions with high demand, ensuring a consistent supply of feed for cattle and poultry. This distribution system creates an efficient supply chain, maximizing the economic value of sorghum and supporting sustainable livestock industries. Leading the world in sorghum exports, the United States accounts for nearly 70% of global sorghum exports, solidifying its position as a dominant force in the industry. This crop is an economic heavyweight, contributing billions of dollars to the U.S. agricultural economy. With over 20.9 billion pounds harvested annually, it supports farmers, processors, and industries across the country. Beyond its economic benefits, grain sorghum holds a special place in American agriculture and culture. Sorghum syrup, a traditional sweetener in the American South, adds a nostalgic touch to pancakes and biscuits, carrying on culinary traditions passed down through generations. In daily life, grain sorghum quietly contributes to everything from the cereal on your breakfast table to the fuel in your car. Its ability to thrive where other crops fail stands as a testament to the ingenuity and unwavering determination of American farmers.